Right, so we've learned how to design the beams already. This would be kind of a third method, and I'm not going to go through this method. You have it in your notes if you want to go back and look at this sometime. But as you can see, it's already pretty quick to do designs and try different sections using the methods we've already learned. I mentioned this briefly that there's a way you can estimate and just say 0.9 J, or 0.9 as J. In other words, 90% of the height would be equal to approximately D. And you can use that to do your flexural design. I'm not going to go through this because it is not any faster and it's adding to the number of methods you need, and this is an approximate method anyway. But I'm going to leave this in here because you will possibly be in a design office where they like to use the starting point at 0.9 or as J equals 0.9 or 0.9D, or D equals 0.9H, sorry. But in general, I don't think this is much faster than what we already did. So I'm not going to do that example. There's some other information in the TMS that we've kind of talked about. I was just giving you a span length on the last beam, but if you actually want to go in and design, let's say we've got a doorway and we've got the lintel piece over the top, right? And this is wall. I've got a couple things here. I've got a clear span, and I also, what's my design or effective span? So it tells you what that is. If it's not built integrally with the support, you take the clear span plus the depth of the beam, or not to exceed the distance between centers of support. If it's continuous over supports, you take the distance between centers of support. So if let's say I've got this beam and it's resting on two supports here, okay, I'd go from half to half. That would be my effective length. If I have it all integrally done, I can do clear span plus the depth of the beam. Okay, so that would be this amount plus 1/2 the depth on each side. Don't worry too much about this. This is something that you can go in if you're doing this in practice. It'll just depend on the exact situation you have. For this class, I'm going to give you what length to use, okay? So TMS is section 5.2.1.1, or you can go take a look at this in the page 186 of the handbook. All right. Lateral support, it talks about the lateral support on the compression face of the beams. You can go take a look at this one as well in the handbook, same page. We're not doing all the worry about lateral buckling and things like this. This is you just go ahead and you have to have these max spacing of compression face support, and that will typically be put in place. Compression reinforcement, we basically don't bother with that. It doesn't do much for you, so we're not going to talk about it, but if you do it, you have to confine it with lateral ties. Reinforcement limits. We talked about this already when we went through our example problem. There are no reinforcement limits for beams. The exception is some of the special shear walls and seismic design is typically when they're talking special, it's seismic design. There's some limits on the vertical reinforcement in the cell for essentially for the wall pieces. But again, it's a fairly small number, and we use that as kind of our rule of thumb in the last beam example we did. Again, somewhat arbitrary. Okay, so the minimum steel areas, it's basically you just need enough to resist shrinkage, but it's because it's so stable, there's not much shrinking because when I have, as opposed to when I do a fully concrete wall. Okay, so pretty basic stuff there. We talked through, I showed you the page in the handbook where we also had bars and spacing, and that same page has the hooks and laps and all these types of things. We're not going to go through this. This has a lot of detail, just like doing development lengths in reinforced concrete. So you have seen a lot of what this stuff looks like in the ACI 318 code. And so I'm confident that if you want to get down into this detail and you're doing a lot of masonry design, you can go check this stuff out. Okay. Same thing, clearances. We talked about the clearance one on the example problem we did. Cover all these different types of things. And if we had to do steel detailing on this thing for continuity, you see it starts to look a lot like the diagram we have in 318. The setup of the code and commentary in two-column format, the drawings and all this stuff, it's not accidental that they're similar to 318. Let's keep in mind that the TMS was actually an ACI committee for quite a long time. It's fairly somewhat recent that it's been separated out and gone through the Masonry Society pretty exclusively. Yeah, it's still sold at ACI, but now TMS has their own committees. All right, so what we can do is do one more beam design, and you see here, I'm just putting these examples on supports, and so you're going to use the span length I give you. All right, so this is a similar one to what we did before. We're going to have a figure out the tension reinforcement. So we don't have the bars given to us this time. 14-foot long. It's a CMU, so concrete masonry unit. Same cross-sectional dimensions. And they've given us the effective depth they want us to use. Typically, this is only going to be one layer of reinforcement in these things. So giving us the D is a reasonable thing here. It does have a superimposed live load, and it's already in pounds per linear foot. And self-weight, no other additional dead load. We've switched up here. Now we're going to use 2500 as our masonry strength. And we're still going to use the standard grade 60 bar. All right, so let's do this by the KF. You can do this by either of the methods I showed you. I think I'm going to stick with the KF method when I do this one. So I'm going to do this beam design as a separate video just so you have that in the example section.